Now let's start the energy and climate panel. We have three outstanding speakers. I will introduce them one by one later. But let me start from the first one, Professor Steven Chu, again, another Chu, to kick off the morning session. Steve is another leader, both academia leader as well as government leader. Steve is a professor of physics at Stanford University, and I think the audience right here all know Steve. His contribution, actually multiple contributions, one of them was recognized with Nobel Prize in 1997. His multiple other works are equally impressive. I won't go into the detail of that. And in 2009, Steve did a detour of his career. He was appointed as the Secretary of Energy during Obama administration. And as a postdoc, actually faculty member at that time, I was thinking, looking at Steve's career trajectory, why Steve would like to take a position like this. It's really a reflection and retrospect. Steve already has seen playing leadership role in the government can do great things to the nation and also to the whole world. Now let's welcome Steve Chu to the stage to give the keynote speech on energy and climate. Steve.
So it's a pleasure to be here. And if those of you who know me, you're something a little strange. I didn't come with a computer. I meant to. In my rush to get here, I forgot it. So this is going to be unscripted. I've been told in public life sometimes you have to speak without a teleprompter. But anyway, before I start what I was going to talk about on climate change, I would like to tell you a little story. Things are very hard for Asians today. And you think with the China Initiative, the resurgence, as Judy Chu said, the resurgence of the Chinese Initiative, we shouldn't take anything for granted. But let me tell you a little story about my own family. I come from a side of academics, both on my mother's and father's side. In those days, this is the turn of the other century, you would do well in an exam, you'd go abroad, you get educated in Europe and the United States, you come back, and you work as a faculty member or in government service. And so what happened is my father and my mother, during World War II, went to MIT to go to graduate school in economics for my mother and in chemical engineering for my father's side. But what happened was when the communists took over, the academics were not to be trusted, and they knew the ones in China who had PhDs had to leave, and the ones in the United States getting PhDs knew they could never go back. By the time the Communist Revolution got to the Shanghai area, it started in the north. My father's father was old. He died of natural causes. But by the time they got to his house, they needed to make a statement. So they killed the oldest male child of the family, who happened to be 21. And so that's how serious this was. Now, my grandfather on my mother's side was a brilliant civil engineer. He got his doctorate from Cornell, became a university president at the early age of 30, but again, at the age of 49, 50, he realized he had to leave in 1949, he had to leave and flee for his life. So he shows up in the United States. He knows English because he went to graduate school in the United States, but he's no longer a university president. He knows he can't even get hired as a faculty member. And so he told us when we were little boys that he had to relearn civil engineering. And so he started walking up and down the bridges in Manhattan, that connect Manhattan to Brooklyn and Queens and things like that. And was not only able to survive before he died, he got the highest award of the American Civil Engineering Society. But it was a hard life because he really had to start from zero. My father's oldest sister got a PhD in organic chemistry, was a full professor at Beida, Peking University, during those years in the 30s, was thought of as the most influential woman organic chemist or organic chemist in pre-war China. She comes to the United States, a woman, Chinese, can't get a job, suitable of her accomplishments. So finally she gets a job in a small school meant to teach young ladies how to be grade school and high school teachers. That's all she could get, but she's nevertheless brilliant and applied for National Institutes of Health funding, and for the next 25 years she got funding in a place that never had research. So this poor school had to figure out, oh, well, you need to make lab space. In those days, the NIH would actually give you money to make lab space. And so again, very, very hard on people. C.S. Wu, who many of you know, narrowly missed getting a Nobel Prize with Yang and Li on paradigm non-conservation, was a star graduate student at the University of California, Berkeley. A Nobel Laureate there, Emilio Segre, said, this person is fantastic, we've got to hire as a faculty member, but the chair of the department said no, under no circumstances. Why? Because she was a woman and she was Chinese. So she had to go to Columbia University. And so there was this thing, so things were bad then, things were even worse before. Things have gotten much better, and so this conference, this gathering, is to help remind ourselves, but also others, that immigrants in American society have really transformed many parts of society, in science, in education, in industry, in entertainment, in music, things of that nature. And so in the celebration of all these things, I'm lucky. I was born in the United States. I didn't feel the pressures and prejudices that my parents and their siblings felt, or their fathers and mothers. So we should remind ourselves and each other that how important it is. One statistic, if you look at the graduate students in science, technology, engineering, about a third of them are coming from China. And what we see today is an active effort to begin to not give visas to Chinese graduate students. And when I see this, I say, it's shocking. What are we worried about? We're worried about academic spying in key technology areas like nanotechnology, AI, semiconductors, batteries. And then I look around and say, this is strange. Most of the leaders in the United States, or many of the leaders, if not most, many of the leaders in the United States in those areas happen to be ethnically Chinese. So what are we doing to our future is the question. And I hope I'm trying to get voices within industry who are industry leaders, CEOs, founders of companies, or CEOs of major companies, to speak out against this, that we will be cutting off our nose. Okay, so let me switch gears and talk a little bit about energy and climate change. We, this year, have passed 1.5 degrees. That was a goal of the UN IPCC Conference of Parties that said, you know, under no circumstances do we want to go above 2 degrees, and if possible, stay below 1.5 degrees. So we're over 1.5 as of this year. From January through June, it's the world's record temperatures. There's very little doubt among people who've actually studied climate and what we know about it, doubt that the climate is changing, and in large part, if not all of it, really due to human emissions. But we also hear of pledges from our political leaders saying within 2050, we pledge to go to zero carbon emissions. But it's hard, and unfortunately, we will not go to zero carbon emissions. Why? It's because there are certain things we don't really have deployable solutions at the moment. For example, in agriculture, where half the arable cultivatable land in the world is now being cultivated for agriculture grazing, but there's huge greenhouse gas emissions from the raising of food to the emissions from using fertilizer. You put fertilizer in the soil, what doesn't get absorbed by plants comes out as N2O, a very potent greenhouse gas, 300 times worse than carbon dioxide, and stays in the atmosphere 100 years. So we're a world of 8 billion people, and without the third agricultural revolution, which is a mixture of the ability to make nitrogen-based fertilizers using the so-called Haber-Bosch process, 2 Nobel Prizes, and the cross-breeding of plants, for example, Norman Borlaug, a Nobel Prize in Peace for that, we were able to feed a world of 3 billion, now 8 billion people in better conditions, even though the amount of land put under cultivation for major grains remained the same. Again, 3 billion to 8 billion, same land. But we're going 8 billion to maybe 10 billion, maybe 11 billion, and the question is, can we do this without fertilizer? And the answer is no. Organic farming is something for rich people in rich countries, but if you're in the developing world, the idea of not using fertilizer, your food system would break down. So how do you do this? Well, it may be a biological solution. You put in microbes that enter into symbiotic relationships with plants, like legumes. Soy plants can, with their interaction with microbes in the soil, can get nitrogen-based fertilizers and feed themselves. And so there are experiments going on. It's already been done with corn, but it only eliminates half the fertilizer, and it took too long to develop. But we need to do this not only for corn, but wheat, rice, everything. So that's one challenge. When we will get there, what the solutions will be, I'm not really sure, but I am sure it's not going to be 20 years because it is a research area. You heard about all the good news about solar and wind. They're continuing to drop down in prices. All good news, but then we're realizing with 20% solar, you don't need energy storage. There's enough standby power from the traditional sources. But once you get to 60, 70, 80%, you do need several days of storage. That doesn't sound like much, but it's literally about 30 times more storage than we have right now in terms of batteries. And so we are in California 70% carbon free in terms of electricity, but we're beginning to see a real dearth in energy storage in forms of batteries in addition to hydropower. So that's a real concern. But there are other concerns that perhaps not as many people are focused on. One of the concerns is our Earth is finite, we have finite resources. And if you look at all the materials we're using today as we grow economies, it turns out that there's going to be looming shortages. Of course, you probably all know about the nickel and lithium and cobalt shortages for batteries. With better technology, better ways of extracting lithium, for example, out of seawater, I think that could be okay for a few hundred years, but not more. There's something else. We will face a copper shortage. And with increased electrification, this is going to be a problem. Right now, copper, in fact, is valuable enough that people loot buildings to steal copper from buildings. Nobel Laureate John Mather, who worked at Goddard Space Science Center, was telling me a couple of months ago that during a thunderstorm, one of the buildings got zapped, and they were wondering, how can this be? We have lightning rods, you know, what's going on? And they inspected the lightning rod and found that someone had stole the copper, going from the lightning rod into the ground. And so that's how valuable copper is, and the looming shortage. And as a challenge to all the bright people out here, we know that you can make carbon conductors that are within a factor of 10 of the conductivity of copper, but much, much lighter. So in terms of conductivity per unit weight, it's much better. If you can make a conductor of copper, there's unimaginable amounts of carbon in the ground. If you think of all the stuff we extract from the ground in terms of just tons of stuff per year, it falls into two major categories: stuff we build with, asphalt, concrete, cement, and energy, oil, gas, coal. Then a factor of 10 below that, steel, and a factor of another 20 or 30 below that, all the other metals. And so we have so much carbon in the ground, just imagine turning a small fraction of that into wires, conducting wires. We won't have a copper shortage. There are many other areas that I can talk about. I just want to end on one, and that is, where are we going? If you look at, people are talking about the transition first from wood, then to coal, then to oil and natural gas, and finally to a mixture of renewables, maybe nuclear power, hydro, other things. But if you look at the world and what it's really doing, every time there's a new source of energy, we simply add it to it. We're not decreasing the amount of coal. We're not decreasing the amount of oil and gas. It's just being added. And so as more and more solar and wind go online, it too adds. So this is telling us something. How much can we stop adding due to efficiency? I don't really know. Maybe twofold, but not tenfold. And so there's these issues of what's going on. I personally think the trajectory we're on today will lend us about 3 degrees with wide error bars. It could be 3.5, it could be 2.5. It's not going to be 2. And so the concentration of carbon dioxide, now at about 410, 15, 20 parts per million, will go much higher. And one of the things I've become very convinced about is we will need some technology to capture carbon from point sources: cement, plastic, steel, power. But we also will need to capture it from the atmosphere. Because if we're going to 500 or 600 or even below parts per million, the strange weather we're seeing is quite alarming. We don't know how alarming it is. These so-called atmospheric rivers, we don't know whether they're just a fluctuation or they're really going to be there. If they're really going to be there in the future, our whole water management system has to be redesigned. Because in severe flooding, we just dump the water into rivers and ultimately into the ocean. But if that's the water we're going to get, we're going to have to preserve those precious drops somehow for agriculture. So lots of challenges. Carbon dioxide capture is one of them. I'm personally working on that and very excited. We're about to submit a paper today or tomorrow. Today's taken. For a new way of capturing carbon dioxide, which we think will be at least a factor of 30 less energy than the old technologies, and also smaller volumes, very, very scalable with very inexpensive materials. So there's a hope that maybe this could provide a partial path to lowering the carbon dioxide in the air. It can go on forever. Out of time. If I were scripted, I would be better on time. But let me just say that, again, there's so many exciting things happening in climate change. I don't think people are fully aware of the dangers, and that it will take half a century, maybe 3/4 of a century, to turn the economies of the world around. But that means we have to start hard right now. But thank you for listening.
Well, thank you so much, Steve. We'll invite you back just in a few minutes. Now, let's move on to the next speaker, Professor Arun Majumdar. Again, Arun represents both academia leading person as well as doing a leading job in the government as well. Arun is Professor of Mechanical Engineering and also Professor of Energy Science Engineering at Stanford University. He also served as the Dean of the Dow School of Sustainability. That's a school Stanford started about 2 years ago. Really try to bring all the expertise together to address the grand challenges of sustainability. Arun is a member of the National Academy of Sciences, a member of National Academy of Engineering. Arun, during Obama administration, also served as the founding director of ARPA-E, a very important funding agency started in 2009. With that introduction, let me bring Arun to the stage to give you, an overview of what's happening in the Dow School of Sustainability. Arun, please.
First of all, I want to thank Yi-Chui, Kylie, and the whole team for this long overdue meeting. Let's give them a big round of applause. So I know that Steve didn't show slides, but don't worry, Steve. I borrow his slides anyway, so I'm going to show. So I was asked to talk about the Dow School of Sustainability. So what I'm going to do is to show a little bit about why. Why did we do this? And what is the school and how we are thinking about the future. So first of all, I want to show why. Why is this an issue? First is population. It took about 1 million years for the human population to increase to 300 million. And literally over the last century, you have this growth in population, and it takes 13 years to add 1 billion. And by 2050, the population is going to be 10 billion plus minus half, and by 2100, I'll be gone, but many of the young folks out here hopefully will be there, 11 plus minus 1. The Earth has never seen anything like this before. This is a massive, this is not an exponential increase, this is a super exponential. I call this the human tsunami. There are others. There's a human consumption tsunami, and I'm presenting it in terms of GDP. The reason I'm presenting consumption in terms of production because someone is producing because someone else is consuming. So the outer curve is a per capita GDP. That is also super exponential, and if you multiply that with the population, it is, I don't know, ultra super exponential. And we seem to have pegged our success to GDP. Now, Steve and I were deeply involved. Steve was leading our effort to stop the BP oil spill, the leak, if you recall, in 2010. Now, think about it. If there's an oil leak, the GDP actually goes up because you have to spend money to clean it up. That's not the right metric of human welfare. But nevertheless, that's what we get. And to produce these things and to move goods and people around, we need energy. And I'm presenting this over the last 100-something years. I was born in the 1960s. That's the third arrow from the left. My kids were born in the 1990s, my parents in the 1920s and 30s, and my grandparents in the turn of the century. And right before that, that green patch is when Sadi Carnot was developing second laws, and first and second laws of thermodynamics were created in the 1850s. In a matter of just 4 generations, we have completely transformed the way we use energy to produce and move things so that to feed the population. This is what's going on. And it is 80% based on fossil energy. And it should not be a surprise at all that we have a CO2 tsunami. And I can go on and on. There is a water tsunami, mostly for agriculture, to feed us. There is a food going on. This is meat consumption, and as the income levels go up, the meat consumption goes up, and for every kilogram of beef, there is about anywhere from 70 to 100 kilograms of CO2 emissions, and other biodiversity loss. Talking about biodiversity loss, this is a projection that if we don't do anything, we would lose most of our species by the middle or the end of the century. This is pretty bad. We've got to do something about it. So people have realized this. The Paris Agreement that we now have for climate was an acknowledgement of the problem. And we're going to have a 10th anniversary of that next year. So this is not just an energy problem. This is an energy problem for sure. What happens in energy affects water. What happens in water affects food. What happens in food? Biodiversity. That changes our ecology. That changes our health. And climate change aggravates everything. These are the summer temperatures that are measured. These are not projection. These are measured by NASA. Some summers are hot, some summers are cold. But if you look at the distribution is moving to the right. The average is 1.5, as Steve mentioned, and the average is moving up. But it's the tail, it's a proxy for the tail of the distribution. And that tail has a disproportionate effect on people's lives, on their economy. And that's what's going on. So one has to look at it not just as an energy problem, because if you don't think about the water and the other things, you could have unintended consequences. And we are living in the unintended consequences of the 20th century. So what do we do about it? So this is an acknowledgement of the problem. And if you look at what happened in Paris and then in Glasgow, countries have made commitments. China is committed to produce a net zero economy by 2060, United States 2050, India 2070, and all of them. It's the race to who can get there faster, which is fantastic. 66% of the Fortune 500 corporations have made some kind of a net zero or climate commitment. And the United Nations has come up with Sustainable Development Goals. But he asked the question, are there plans to navigate this transition and get to net zero? The answer is mostly no. Next year, in COP30, all countries are supposed to propose their plans on the transition and what the policy framework ought to be. And this is work in progress at this point. That's the world we are living in. We need knowledge. We need solutions. We need creativity in really addressing, I would say, the defining challenge and the opportunity of the 21st century. So at Stanford, we said, okay, we got to do our part in this, in academia. Stanford has 6 schools, engineering, business, education, medicine, humanities, and sciences. And we had a School of Earth. We ended the School of Earth and brought many elements to the Door School. And so we created the Door School in a different way. Because this issue of climate and sustainability and Earth is not just a business issue or an engineering or law or medicine. It's all of the above. Universities are not quite structured in a way to address an issue this complex. So we got to create an all-campus effort. And that's our job out here, is to be the stewards on behalf of Stanford and the community to create this effort as an all-campus effort, to reimagine academia and tune it to this challenge that we have in front of us. So I won't go into the details. It took 5 years through COVID that we launched this. And I just want to give you how we have structured this. I call this a 3-legged stool. We created a school because that's one of the norms. We can't throw away all the norms. And this is where we hire faculty. We need new faculty. We're going to hire 60 new faculty. This is where we admit students. We offer degrees. We develop curricula. We need new education on how to think about it. And this is where discovery-focused research, driven research is done. And discovery and knowledge is very important for the long term. We cannot forget that this is not either or between that and solution. It is an and. In addition to that, and by the way, just so you know, we have about 140 faculty members from within Stanford. Half of them are joint appointees. I'm a joint appointee with engineering. So essentially, this is a microcosm of our campus to make it an all-campus effort. For those people who decided not to join the school, which is perfectly fine, we had created, under the leadership of John Hennessy and John Etchemendy, institutes which are by definition an all-campus effort. These are institutes bring faculty and students and staff from across campus to do solutions-driven research, long-term research. And we have two institutes, the Woods Institute for the Environment and Precourt Institute for Energy, and we plan to launch a third institute on sustainable societies. Now, we have been doing this for a while. What we found that there's a gap. What we often do on campuses is to do proof of concept. Someone has an idea, and we prove the concept. And that's perfectly fine. But there is a gap between that and the impact outside. And what we felt we were missing was the idea of how to scale things. How do you show proof of scalability? Because if things don't scale, they may not matter. And so we launched an organization called the Sustainability Accelerator, and it's being co-led by each way. And this is to nurture those solutions that are scalable and then launch them out there. And so let me give you a little bit of how we are thinking about it, and then I'll finish up. So we are a bunch of faculty, students, and staff, and postdocs, and that's what a university is. But there are some big problems out there that we got to address. We call them our flagship destinations. And just to give you the first one that we launched, it is to remove atmospheric greenhouse gases at the gigaton per year scale within a certain time frame at a low cost, right? That's our goal. And it has to be gigaton per year. And by the way, the lifetime, as Steve mentioned, the lifetime of CO2 molecules is several hundred years. And so there's a lot of garbage that we've already put out there, and if you don't remove them, we're not going to be able to maintain 2 degrees, as Steve mentioned, leave alone 1.5. And so we got to remove that. So how do we do that? There are many, many different ways, pathways, but what we have to do is to then point out the gigaton per year and then work backwards as to those solutions that are scalable. And when you work backwards, it is not just a technical issue. There are policy levels, there's finance, policy, markets, all of them have to be thought together collectively. And then if there are gaps in several of them, we got to fill those gaps and bring them together. And that's how we are launching. And there are many other things that we're looking at. Fresh water. There are issues related to grid-scale storage and many, many others that we have to do. So this is how we are thinking about it. We have a North Star to use everything we have to lean into this with the fierce urgency of now. There's a quote that I really like. It's an indigenous quote about how we should think about the future. And I've used it so many times, my staff decided to paint it on my office wall. I said, okay, that's fine, to remind everyone. And the way to think about the future is, we do not inherit this earth from our ancestors. That's the wrong way to think about it. We are borrowing it from our children. And let me end with that. Thank you so much.
Thank you very much, Arun. Let's move on to the third speaker, Professor Chen from MIT. Let me just say a few words. Gang is the reason to bring us together back in 2021. One FBI wrongly arrested gang that woke up the whole scientific community, particularly Asian American, Chinese American community, self-organized. After that, we launched Asian American Scholar Forum, AASF. We hope government will not make mistakes like this again, and we want to work with the government to do the right things. So Gang's leadership, of course, painfully from his own experience to bring the whole community together. Gang is a top scholar. He's a member of National Academy of Sciences, also a member of National Academy of Engineering. He served as the department head of mechanical engineering at MIT. And let's welcome Gang to the stage to talk about his new idea on energy.
Good morning. I would like to thank Yi and thank Kai for organizing this wonderful event. And I want to also echo Congresswoman Judy Chu to mention the Franklin Tau case, because we know Franklin has fought very hard, and he's still on. I know his wife is here, and he's here, and they still own the law firm $1 million. So I would like to call our audience to support him. And with that, I know that following Steve and following Arun will be a really difficult act. And so I thought about, rather than talking any big picture, I'm going to talk about a small picture, a science, a detailed science. And I'm going to talk about evaporation. And this is something that we all experience every day. We all know. And we know that evaporation needs heat. And in fact, we call evaporation thermal evaporation. But today, I'm going to tell you there's something we do not know yet about evaporation that is happening every day. And I'm trying to convince people this is happening. So I'm sort of really at a very, very early stage. And I want to share this with you. And Arun talked about water. So I work on evaporation. I work on water. And before this, I never touched, say, this kind of topic. In fact, I work on heat transfer. Arun is actually my academic brother. We had the same advisor, Professor Chancellor Chen from UC Berkeley. But I would work on solid. But since what happened to me, I decided I'm going to switch the topic. I'm going to stop all my previous research. I'm going to, I no longer seek government funding. Because it's just, even with the policy, we work very hard to, say, really talk to the government and make sure the policy, we have a seat at the table. But I myself, I've decided I'm not going to seek government funding. So I changed my topic. I'm going to talk about water. So let's go to the next slide. And we all know water is essential for everyone and everything. For life, we're made of 90% water. And right now, there's 65% of the world population experience water stress. Living in California, I don't need to mention it because you know you are limited how much water you can use in watering your lawn. But by 2050, there are another billion people going to live under extreme water stress. And agriculture and the electrical power consumption actually use 80%, nearly 80% of the fresh water production. And then if you think about industrial process, evaporating water is very energy intensive. In fact, just drying consumes 20% of the energy usage. So, and I was motivated looking into this problem in desalination and think about the solar desalination. The problem is water does not absorb sunlight. And in fact, on the top figure, you can see that the sunlight, of course, has most of the energy at the green wavelengths. And at the green light, the light can propagate 40 meters. We are all very happy to see the clear water bottom because we like clean water. And so, but for desalination, we want to heat up. If I think about the solar, heat up the water. So one way we came up about 10 years ago is to float. It's very simple because we need a simple solution. We float some black porous material on water surface. And in this case, we know it's a simple thermodynamic exercise, how much sunlight energy coming in, and how much energy we need to evaporate a kilogram of water. And then we know there's this limit about 1.5 kilogram per meter square per hour. So we published a paper, we moved on, but the community picked it up, and a lot of people start working on floating different materials, trying to improve the efficiency. And I never thought there would be anything special out of this, trying to get the limit. But then, 4 years later, in 2018, Professor Guihua Yu from UT Austin, that reported they put a hydrogel, black hydrogel there, and they can reach over 3 kilogram per meter square per hour. And the first reaction I had is, this is wrong. I brushed it aside. But then in 2019, I had a visiting postdoc from Shanghai Jiao Tong University, and he wanted to work on this topic. And I remember Guihua's work. I said, why don't we try to repeat it? So it took about 6 months to repeat, and with Guihua's help, in fact, and they were able to repeat that we actually got convinced. And then we said, let's try different wavelengths. Is there any special? Because there's something really strange here. We want to find out, we want to understand why. And to our surprise, we saw a wavelength dependent. It actually peaked at the green wavelengths. Here is the peak, and you can see it's really strange. It's above the thermal limit, it peaked at the green. And green light, water does not absorb. And in our sample, we have black absorbers, so we thought that something maybe related to thermal. So this really was strange and took us a long time. And in fact, I'm proud that during the year of 2021, the darkest time in my life, I was just doing MIT was generous and allowed me to have library access. And so I read a lot of papers and thought about what's going on, and came up with a possible picture. And that is, in fact, really inspired by a lot of other papers that showed that different materials all have this super thermal evaporation, and then realize the thing that's common is those materials have a lot of surface area. So I started thinking whether there's surface effect, and I was inspired by the photoelectric effect, because the photon come to metal surface and lock out the electrons. So I start to think about the physics possibility of photon coming to water surface and lock out not a single water molecule, but a cluster of water molecules. It's just like light can spray water into air. And the picture here is actually more complicated. It's still hand waving. It's based on Maxwell equation. And think about over water-air interface, there's a sharp change of electric field. And basically, over a single water molecule, the hydrogen atoms and the oxygen atoms experience a different force because of this change of electric field. So with that, we start to do different experiments. In fact, we have done 20 different experiments. I don't have time to talk about it. So I'm just going to show 3 examples. One is that we use a green laser. And in this case, because we need an electric field perpendicular to the surface, so we need to have a light come at an angle. And if light comes perpendicular, just right at the surface, perpendicular, the electric field is parallel to the surface. And that effect doesn't exist. And when we measure temperature rise, at the lower incidence, this is a green laser, we don't see temperature rise. But when we go to higher angle, we see the surface heats up. And it only heats up it's mostly due to when there is the electric field. This is a TM, transverse magnetic field, that has an electric field perpendicular to the surface. So that is one evidence. And then we measure the air side temperature, so it's just temperature distribution above the water surface. And what is interesting, you can see when we turn on the laser, the air cool down. The light actually cool down the air. And then there's a flat region. And when we turn off the laser, air heated up. And the reason is like what I say, light spray lock out the water molecular clusters into air, and they cool down the air, and they saturate the air, so the temperature has a flat region. And I was going to stop here, but there's one more I think I have to tell you. And this was because after I had this idea, I couldn't talk to anybody because the judge said I couldn't talk to any potential witness. So I just stopped talking to anybody. And I was the only person I could talk to was my wife. And she's an accountant, right? So, and first I told her the idea, and she said, are you sure people don't know this? And I said, I'm sure people don't know this. And then I finally convinced that this could happen, and she said, you're just copying Einstein. And finally, and she said, oh, when the weatherman said, after sun burn the fog, I said, we can do an experiment of a fog. So we went to make a fog on, say, just generate water droplets, and then we shine light of different wavelengths, right? And we should not heat up fog because green light doesn't get absorbed. But we actually can heat up the fog. And so I didn't know at that time that there is an 80-year mystery in atmospheric science. People have measured the cloud absorbs more sunlight than any theory can calculate. And there are a lot of arguments in scientific literature because measuring the cloud absorption is very difficult. So we think we have an answer, but of course, this needs to further prove it, and I'm actually doing a lot of modeling myself. And so I just want to share this little story, and because even though this evaporation is a daily phenomenon, we think we know everything, water is so complicated. It's really interesting when I try to read, understand literature. And this observation, discovery we think I had a lot of implications, right? I have listed some of this, and in fact, there was a YouTube video that was put online, just somebody I didn't know, and over a month ago, now it's almost a 2 million hit. So you can see people are interested in this, and there are people asking the same question we ask, why we live in a green world? Is there anything to do because we observe that under green light, this effect is actually strongest? We have no idea. We're still trying to understand why this is happening. But with that, I will stop here, and I want to thank thank the audience for you being here. And as a member of AASF, I'm very proud what the AASF have done, and together, as Kai Lee often say, together we move mountains. Thank you.
Well, thank you, Gang. Let me invite Steve Chu and Arun Majumdar back to stage. We have a little bit of program change. Please sit down, Gang. So it's the break time now, but we are not going to have the break. I'd rather give you the time you could participate in panel discussion. So I'm going to do Steve, Arun, and Gang, if that's okay. I know audience are eager to ask you questions. We're going to do a 15 minutes roughly of Q&A. I'll ask probably about 5 minutes questions, and then I'll open this up to the audience. You love to interact with the keynote and the panelists. I guess I'm going to sit down as well to make it easier, so you don't have to look at me back and forth. So I will start by asking the first questions. If you will name the top 1 or 2 technology we need to invent to make a huge impact in the energy and climate space, what will be your favorite choice? And I know it's a hard question because I don't only give you 1 or 2, not 5 or 10. Steve.
Well, I've already said them. I think how do you increase productivity in agriculture but without the N2O emissions and the methane emissions would be the first choice. And CO2 capture. 1/3 choice, if we can get a battery that charges 200 miles in 5 minutes over a 300-mile range, that's twice as cheap. EVs will just become the natural choice. You go back to service station model, and everything will be good.
Arun?
One is a really tough choice, but I would say if you could figure out a way to remove CO2 or greenhouse gases, especially CO2, and use that to create the fuels. Of course, you need hydrogen or some kind, or maybe not. E and I are working on a project that I think will create a fuel that does not need hydrogen. I think that creating the circular economy on the fuel side, I think the electricity sector is getting decarbonized. It has to get decarbonized with renewables and nuclear energy efficiency, et cetera. But I think the fuel side would be very, very important.
Gang?
So they already have the choice. So I just say what I'm working on. I think another real important problem is AC, air conditioning, because if you think about the AC since carrier invention, the efficiency improvement is so slow. It's about 1.9% per year. And now by 2050, we'll have to increase the capacity by 4 more times. And so can we double, can we triple, quadruple the efficiency? Really, that's very important in terms of the CO2 reduction.
Yeah. So talking about energy technology, to make a global impact, we need scale. And traditional academia, Arun, particularly in your slide, you show Steve Chu's slide, is how do you go about change academia and orient into a way to address the scaling issue right from the beginning? Any thought you can share, 3 of you? How do we do that?
Well, I think, academia, the way we educate, let's say I'm in engineering and I'm interested in thermodynamics. I mean, by the way, we share the same advisor, as pointed out, Chen and Tian. And, we have an empty seat out here. Let's invoke him, let him be the avatar of Chang Lin, and always ask the question, what would Chang Lin do? And I'd like to think of our challenges ahead from that perspective. I really think that we talk about the fundamentals, and which is absolutely critical, but we don't step out and think about scale. We are developing a curriculum on scaling out here at Stanford, which will make it available for everyone. Because when you think about scale, from the beginning, there are some things that will scale, some things that will not. And it's very difficult to know a priori which ones will or not. So things like how much headroom is there in technology using science and engineering to reduce the cost, right? If it does not go down below a certain point, it just will not scale. Is it infrastructure compatible, or would it need new infrastructure? Infrastructure takes a lot of money and time to build. If you can make it infrastructure compatible, it'll scale faster. How much money would you need? What are the return on this investment? What are the policy barriers, regulatory barriers that you have to overcome? And once policy levers that you can utilize, public acceptance issues, markets that are available, or co-benefits that you can get. And I think those are the kinds of things that one has to think holistically to figure out, which problems to solve. Now, let me also add that we should not be solving or doing research only with that mindset. I think we need discovery-focused, knowledge-creating research so that you can do the latter. But I think we need to introduce some elements of that scaling into our research and education.
Steve.
I think to add what Arun said, one of the things that we can anticipate in scaling is if you think it's going to go over very large things, does it require materials where there will be a materials issue, material supply issue? Electrolysis with precious metals simply is not going to scale. We all know that. There's enough lithium for EV batteries for 100 years maybe, but not for utility scale batteries. So again, we already know that because of materials resources, you won't scale. And so those are some of the things that immediately academics may not really be, they're focused on getting out a new mechanism, new paper, all very fine and good. Again, to Arun's point, using an old catalyst to do something differently new could lead to some discovery where you can go seek for an earth-abundant catalyst. But of the things that you want to take to scale, you have to look at the materials. For example, carbon versus copper that I talked about.
Gang, any comment on this?
No more. I just thought, as a regular faculty member, we need to change the incentives, right? The funding model, and there are some effort. I really like, Arun and Yi, you're doing on the accelerator, and think about the 1 gigaton per year, right? If you can't reach there, don't talk about it. Well, you can still do your private, research, like what I'm doing as a regular professor, but the funding guidance to this is very important. It's a stimulus. And I thought that in really bridging this gap, having the entrepreneur and the faculty working together. I always thought that in U.S. that our funding is keep saying that every time we have to have complete new ideas. And once you demonstrate the idea, you go to the funding agency, it's very hard to move to the next step. And that is a bottleneck. We need to change some of these funding models.
Yeah. You know what? I want to open the floor to the audience and see you have questions. I think there's one right here. I can see raising hand already.
Thanks for the terrific set of discussions. I wanted to build on the topic of education and funding. So on the education front, there's the challenge of scale, but there's also disciplinary versus interdisciplinary. And clearly, this is a deeply interdisciplinary problem that requires deeply disciplinary knowledge as well. So should we be changing how we educate our students? And on the funding front, most funding is short-term, not over the time scales in which these solutions are needed. So should we also be thinking about changing how government funding is addressing this critical issue? Thanks.
I think in this area, I do think we need to reimagine education. And the reason I'm saying that is the following, and we are both engineers, and if you think about engineering per se, I mean, we go deep into some subject, which is absolutely critical. But if you think about the way I talked about earlier, what happens in energy affects water, and that affects something else. So there are interrelations. There's a many-body effect, which is very important. And the same thing in engineering and sciences, humanities, business issues, they're all related. And so there's a very famous paper that Philip Anderson, Nobel Laureate in Physics, wrote in 1972 that he published in Science. And I'm saying this with a lot of caution in front of Steve. And he said that chemistry is not physics, because there are many body effects that happen. Just because you know how the atom works doesn't mean that you know how chemistry works. Biology is not chemistry, because there are other interactions that happen that are not captured in the molecular, of trying to understand single molecules or a few molecules. So I think these many body effects are critical. So just because you go deep doesn't mean you can come back and learn how the interactions happen. And there's new science in the interactions. And I think that's, I've read this thing many, many times, and now I said, okay, our education is similar. There are many body effects that we should be thinking about, that we need to capture in our education. And I, kind of flippantly call it the Mona Lisa. Today we are teaching the eye or the nose or the ear, but we're not talking about the whole picture. Now you do need to understand how the eye works or how the ear works, but you also need to capture the full Mona Lisa at some point. And I think that's an addition, I wouldn't say replacement, but an addition to an education system.
Can I add a little bit on funding? We have peer review systems, and they're flawed, but it's the best we have. But I was raised, I was a graduate student, postdoc, in the beginning, assistant professor at Berkeley, but I went to Bell Labs immediately. And then I was raised in a culture where there was no outside funding. The department heads and the directors made the funding choices. You had an idea, you go to your department head, they listen, they say sometimes, no, I don't think this is going to work, or yes, that's a great idea, here's the money. It was instantaneous. When I was the department head, if I disagreed, we would just go to the whiteboard, blackboard, and we'd talk about it. And so what we had at Bell Labs was not peer review, but superior review. The very best scientists and engineers were making the funding decisions in person. We don't have that anymore. Many of the best scientists, they say, I'm too busy. And so one of the things, and that vision of Bell Labs, when I became Secretary of Energy and wanted to start ARP-E, which was proposed in 2005, 2006, enlisted Arun, and he had to listen to me rave about Bell Labs the whole time I was the director of LBL. And I said, I want the people giving out the money to be smarter than the people they're giving it to, that they have to be able to recognize something long before it's fashionable. Before, peer review recognizes things that are established. And new ideas rarely get recognized except by very few of the smartest people. They say, that's a new idea, that's not incremental. And so Arun, with my help and others, assembled stellar reviewers. And it was remarked that at a ARP-E summit that these guys are amazing. They are smarter than the people they're funding. And not only that, they're just not funding agents. They have quarterly reviews. They go in there and they help them solve the technical problems. You don't get this in federal agencies for typical funders. And so if we can somehow get it so the very best people can give their time. I only spent 20% of my time as a department head. The rest of the time I was in the lab doing work myself. If we can get those people to spend the time, that's where it will really dramatically increase. Whether it's multidisciplinary or everything else, the smartest people can recognize something new and worthy of funding, rather than saying, okay, it's not going to work, it's not working. You essentially have to get seed money to make it work before you get funding.
We have 5 minutes. I want to do a rapid firing of the questions from the audience. Let's keep the answer brief. Zhigang, I saw you already have the mic. Why don't you ask?
Okay, this works. So this question is directed to Professor Arun Majumdar. Many years ago, you came to Harvard, I don't know if you still remember, came to my office to talk to me when you were still director of ARPA-E. And you talked to me about the solar cell, the excitement you had for it. Recently, there is an article on solar energy in the magazine The Economist. The prediction really is something along the line you told me about. I want to get your comment on this. The prediction was by 2040, solar energy will prevail over all other forms of energy. That's first. Second, the prediction is from that point on, the energy will become essentially free. I want your comment. So the new question the article posed, what should we be thinking about in the world when energy is free? Thank you.
Well, Zhigang, thank you. Former colleagues. Well, I think the cost of, when we were in DOE, we launched in 2010 the Sunshot initiative to reduce the cost of solar to be less than that of fossil fuel. It actually was reached in 2017, at least somewhere. I think we are still seeing the headroom in improvement, whether it's perovskite or something else, or in efficiencies being increased. The majority of the cost is not the panel, it's the balance of system. And so the efficiency really matters then, because we're going to install less. And I think the more we do, the cost is going to come down. And I think to the point that free is difficult, right? Because someone has to pay for something, right? But I think it's going to be very, very low. So you will see a huge adoption. Just so you know, by the way, last year, 2023, this is a report from the International Energy Agency. The amount of money that has gone in renewables is almost $2 trillion compared to the investment that has been made in fossil fuel. That's $1 trillion. So it's 2 to 1 already. And that's because it's cheaper. And there are, obviously other implications as well. So I think it's going to go even lower. And we are going to see, this is a revolution. We are sitting through that transformation going on right now. I don't know, Steve. By the way, they have worked a lot in solar as well. So quick.
Well, very quickly, I think solar is cheaper now, but it's all the other systems, the backup systems, the distribution, transmission, and especially energy storage. So the real cost of solar are all those systems. And so it actually has to be at least twofold cheaper than the next natural gas or anything else.
Any comment, gang?
No. You already asked yesterday.
You are convinced? That's good. Let's take one more question. I think these the ladies right there. She's good.
In the last slide, mentioned about the significant questions about your new discovery. I just wonder, which one do you think is more challenging than the others? Especially, I discovered this could be widely used in energy transition, in water, and in heat management. So it looks like this could be very, with huge potential. However, I just wonder what could be, because in each of the questions you mentioned, I think it all requires a lot of research effort. So I wonder what's most important for you now, or what's the most challenging bottleneck for you now? Thank you.
Thank you for that question. And the quick answer is that I'm waiting for the scientific community to prove whether I'm right or wrong. And I'm actually happy to see, at least now, recently there was a paper seemed to doing different experiments consistent with what we have. But we are really scratching our head on the microscopic, physics, what's going on. I only have a hand-waving picture. on the application side, I think actual drying is really where we could have a lot of applications because drying consumes 20% of industrial energy use.
So I'd like to give each one of you 15 seconds. 15 seconds, I'm serious, to advise the young people, a lot of students right here, what do you want them to think about, to do? 15 seconds. Steve.
There are so many challenges to energy transition, sustainability, things of that nature. It is, in my opinion, the most important problem society faces. And I hope you will join and pitch in because you're our hope.
Arun?
Get an education. This is very Asian. Rely on education. And just I would say that what Gang went through, injustice for one is injustice for all. Embrace that.
Gang.
To answer that, I have in my image when I interview at MIT, and Nam Su like to draw a curve U-shaped. One side is fundamental, and the other side is applied, and vertical axis is impact. And I like his, you work on the end, very fundamental, very applied, and that has impact. And I think Steve, Arun, they all work on both sides, but don't work in the middle. Don't work in the middle.
That's very Changlin Tian.
Yeah.
Yeah, that's very Tian.
Yeah, also Chen was saying pushing to the extreme. We all get that story. That's both sides.
With the high notes like this, let's conclude this panel. Thank you very much.
Thank you.